Welcome to Digital Electronics Lecture 2 Part 3. We'll discuss about universality of NAND gate and NOR gate. This concept is very important, so try to give attention. All Boolean expression consists of various combination of basic operation of OR and an inverter. Therefore, any expression can be implemented using combination of OR gate, AND gate and inverter. It is possible to implement any logic expression using only AND gate or OR gate. So that's why NAND gate and NOR gate, these two gates are called as universal gate, because using these two gates, NAND and NOR, you can implement OR and an inverter. Now let's check how we can do it. So just look at here. So this is our inverter circuit, this is our OR gate, this is our AND gate. So the inverter can be implemented using this NOR gate. So this is typical NOR gate. So if you put this connected, the second input, so this will act as an inverter. So if your input is A, so it becomes here A plus A prime. Then using Boolean expression, you can write it A prime. For OR gate, you need to use 2 NOR gate. This is basically NOR gate as well. So A and B, this becomes A plus B prime. Then putting these two inputs together, it becomes A plus B prime, then again whole prime due to this bubble. So it becomes A prime, A plus B. So your inverter, this is your inverter using 1 NOR gate. Using 2 NOR gate, you can implement OR gate. For AND gate, you need to use 3 NOR gate. So 1, 2, 3, inverter, OR and AND. So just look at here, A becomes A prime, B becomes B prime, as it is NOR gate. So it becomes A prime plus B prime, then whole prime, which becomes AB, if you simplify it using the Boolean function algebra. So using the NOR gate, we can implement any of these three gates, either inverter, or AND gate. Look at next one, universality of NAND gate and NOR gate. So here we are implementing inverter and an OR from NAND gate. Just same as before, like 1 NAND gate for inverter, 2 NAND gate for AND, and 3 NAND gate for OR. So A, here A becomes A dot A prime, which is A prime. This is basically inverter. So from NAND gate we are getting inverter. Again A and B. So this is our NAND gate. So A dot B prime, this is our output. So A B prime, this becomes, after this NAND gate, A dot B prime whole prime. So it is become A B. I use the pointer, maybe it will be better to understand. And the last part, or OR gate, so A becomes A prime, B becomes B prime due to this NAND gate, A and B. So here it becomes A prime dot B prime whole prime, which is become A plus B. So for one inverter you need one NAND gate. For AND gate you becomes 2 NAND gate. For OR gate you become 3 NAND gates. So you might think, why you need to do this? Because say you need to implement a circuit where you have a function of inverter and OR, but you don't have these three logic gates to implement that. You just have only NAND gate. So with the only NAND gates, you can also implement these three functionality. So that's the advantage. Okay, so in this example, it says in a certain manufacturing process, a conveyor belt will shut down whenever a specific condition occurs. What is the condition? A logic circuit needs to generate X that will go high if either of the following two conditions are satisfied. Okay, so if condition 1 or condition 2 is satisfied, then logic will go high, then the conveyor will belt will shut down. What is the condition? Condition 1, conveyor belt speed is too fast and collection wheel at the end of the belt is full. So too fast, this is represented as A, collection wheel at the end of the full is B. If this condition is satisfied, then conveyor belt will be shut down. And the second part is or belt tension is too high, which is C, and manual control is off, which is D. So if we write the condition through expression, we can write it X. So X will be high either when this condition is true or this condition is true. As this is OR, so this part becomes AND. So A and B, so A and B, and this one become AND, C and D, C and D, and these two becomes OR. That's why AB or CD. So this is the expression. Okay. So if you draw the expression, so it becomes like this. But A and B, C and D ORing together. So out of X becomes AB plus CD. So the straightforward method will be using two AND gate and one OR gate. Anyway, another implementation can be accomplished by replacing AND gate and OR gate by equivalence NAND gate. So we can also draw it using equivalent NAND gate. It looks like something like that. So this is our expression. So this part, as we discussed before, so this AND can be implemented using two NAND gate, and this AND using two NAND gate, and this OR can be implemented as NOR. So this three NOR gate. So it becomes, so at first glance it looks like it requires 7 AND gates. Just look at here, 1, 2, 3, 4, 5, 6, 7. So it becomes 7 AND gate. However, NAND gate at 3 and 5 are connected as inverter. So 3 and 5, this is basically as an inverter, is double inverting. So this is basically no use actually. And also 4 and 6, this is also double inverting. So there is no use, so we can eliminate this. So inverter in series can be eliminated from the circuit since they perform double inversion of the signal of NAND gate in 1 and 2 both. So we can ignore these two and we can simplify this, just only 1, 2 and 7. So 1, 2 and 7, if we put like this, it will be like this. So instead of using two AND gate and OR gate, we can implement it using only NAND gate. So we can just implement using one IC. So this is simplified version of the previous one. Alternate logic gate representation. Obtained from the standard symbol, invert each input and output of the standard symbol. So this is done by adding bubbles on the input and output lines that do not have bubbles, by removing bubbles that are already there. Change the operation symbol from AND to or from OR to AND. In special case of the inverter, the operation symbol is not changed. It can be easily provided that the alternate symbol is equivalent to the standard symbol by using De Morgan's theorem and recalling that the bubbles represents an inverting operation. So what does it mean actually? To be very clear right now. So you have AND gate. So you can implement the same function using NAND gate, kind of NAND gate. Also, this is the OR gate. So kind of, sorry, actually this is not NAND. This is NOR gate, kind of NOR gate. This is kind of NAND gate. So just look at here, AB. So AB becomes A dot B. So what it says, your input doesn't have bubbles, so put bubbles here. Input doesn't have bubble, put bubbles here. Output doesn't have bubble, put bubbles here. So if you put bubbles, then your and become your kind of NOR, but at the end you're getting the same colors, a dot b. So here a b, that means a prime dot a prime and b prime. This is all function so we're doing. So a prime plus b prime, then for this bubble whole prime. So you simplify that, it will be a dot b, same as it is. So this side you don't have any bubble, give the bubble here, give the bubble here, and give the bubble in the output side. So you will get the same function, a or function a plus b. So how? So your a, this is your AND gate. That means it becomes a prime dot b prime then whole prime. So a prime dot b prime whole prime. If you simplify, it becomes a plus b. So other things is pretty similar as well. For NAND gate, just put the bubbles. So just here, input doesn't have bubble, put bubble here. B doesn't have bubble, put bubble here. And output has bubble, so replace that bubble. So take off that bubble. That's it. And the output here at NAND gate is A B prime. So here it becomes this OR gate. So A prime plus B prime, which is basically A dot B whole prime. So what we called, you replace your basically AND gate using OR gate, or your OR gate using AND gate. Same, your AND gate using OR gate, your OR gate using AND gate, and inverting is an inverter. Just this bubble, just replace this bubble. Input side doesn't have bubble, put bubble here. Output side bubble, remove the bubble. So if this is the alternate representation. Active logic, active logic level. So what it means, each of the logic gate symbol represent a unique interpretation of how the gate generate. When an input and output line on a logic circuit symbol has no bubble on it, that line is said to be active high. Say like it doesn't have any bubble, so this is called active high circuit. This has bubble, so it is called low state output, or low state is the active state. And this has bubble, active low, and this doesn't have bubble, so high state, active state. So what does it mean? It means output goes low only when all the inputs are high. So this is active high, but output goes low when on the input is high, and this says output goes high when any of the input is low. Similarly, output goes low when all inputs are high. This is active high, and this is active low due to bubbles. So output is high when any of the input is low. So this is called active high side, and high state is active state. This is called active low, and low state is active state. So output goes high when any input is high, and for this one, the second one, output goes low when all inputs are low. Okay, so here is two assignment for you. So it says the output circuit in the figure represents output MEM. So this is your output that is used to be activate the memory IC in a particular microcontroller. Determine the input condition necessary to activate output. So to activate output MEM, so to activate this one, what should be the input? Like RD, ROM A, ROM B, ROM C. What should be the input? You need to determine. Just think about that. Whether it is active high and active low. If it is high, then what should be this input? Then from this input, you can determine this input, and from there this input. This is another assignment. It says the circuit will turn on when the motor drive is on. When this drive, this output is on, then circuit will be turned on. So to get high here, what should be the input? You need to determine. So that's your assignment. Try to solve it by yourself. Thank you.